Okay, so welcome back to our channel. Today we will be looking at our first project intro. So today's project, or like the project of interest today, is called tropical differential operators. So yeah, okay. So this comes from a field that is very new called tropical differential algebra. Okay. So the prerequisites for this project, prereqs, is mostly none. Um, if you are a uni student, so say first year of university, or if you just have some basic engineering math knowledge, so that is sufficient. Okay, so yeah, all right. So let's go to the topic of today's interest. Okay, so today's our project's interest is called tropical differential operators. And to understand what this project is talking about, let's start with our most basic thing. Let's understand what a differential is. Okay, what we mean by a differential in this project. So yes, obviously we'll be talking about derivatives. And so it's your standard thing, you have d of dx, f of x is just the limit of h tends to 0 of f of x plus h minus f of x divided by h. Okay, nice and simple. Okay, now the thing is that obviously what do you say, differentiating is sort of like the inverse of taking the integral, right? So what happens is, what happened, oh crazy, okay, yeah, so what ended up happening is that it was harder to given a function f, so say you wanted to take the nth derivative of f of x, like that, d of x to the n. This was a lot more messier. It was not harder, but it was messier compared to trying to generalize the nth inverse integral of f of x dx. Okay, dxn. Right, so what we ended up doing is we said, okay, let's just take the integration notation as just I to the power of n minus. Okay, so this is inverse integration, right? And integration, that's why I. Okay, so we take that as an f of x over here. So now instead of thinking of it as the differential operator applying to this n times, we instead, for the sake of cleaner this thing, let's just talk about this casually. So for the sake of keeping it clean, we instead talked about it as the inverse of integration, and somehow let's just pretend that's the magic and it got easier to talk about n times integration. And this is me basically sweeping everything under the rug so I can get to the basic, so I can skip the basic premise of this talk. Okay, so yeah, everything, let's just magically hope that everything is easier when we talk in terms of integration. And yeah, so if we pretend that I over here is the operator that acts on a function f, then this guy named Cauchy derived the nth repeated integral formula. So Cauchy's integral formula is given as follows. Okay, so for this intro, this is the only part that I ask you to just blindly accept. It is given to you as d minus n by dx. Let's scroll further down. Yeah, x power minus n of the function f of x, which is the same as not I to the power of minus n. Oh yeah, right. This is minus here, correct. So yeah, over here, instead of taking it as n, we took it as minus n. So I to the power of n acting on f of x, okay? And this is given to you by 1 by n minus 1, the whole factorial, the whole integral ax x minus t n to the power of minus 1 f of t dt. So this is under the assumption that f is integrable. Okay, so this is basically what we have to play with, right, for our first definition. Okay, and what we do with this definition is that we use this to generalize and define our fractional derivative, or in particular what we'll be looking at is known as the Riemann-Liouville derivative or formula. Okay, so let's go down and let's just make space for everything. Yeah, there you go. Okay, cool. So the Riemann formula or the Riemann-Liouville derivative is given where n is no longer just an integer. Alright, and now we say n belongs to real numbers, or before that it was originally just said for n belongs to rational numbers, but it's also extendable to real numbers. So how is this? Let's recall that n factorial is the same as gamma of n plus 1. So gamma is a function that is mapped from a real number, which is what n over here, n plus 1 is, to another real number. Or it can also be extended, so by a process called analytic continuation for gamma, you can extend this, its domain of just R, so that it now takes complex numbers and maps to another complex number. Okay, so since this is defined for R, clearly you can say ki, okay, it is also a map from, I can take, what do you say, the rational numbers lie in R, so I can obviously put this in here. Yeah, and so by making this substitution, I just rewrite my Cauchy formula, and I say d minus alpha this time for the let's just take alpha as a real number instead of n. Okay, now we have alpha. Okay, so d to the power of alpha f of x, the whole divided by d to the power of x to the power of minus alpha is equal to I to the power of alpha, or I integrated alpha times on the function f is given by 1 by gamma n, or no, alpha, we're talking about alpha now, 1 by gamma alpha, the whole integral a to x x minus t alpha minus 1 f of t dt. Okay, so this is how it was defined. Yeah, and so far if you feel lost, that's fine, because all I've been doing is I've been just spewing integral after integral while not really giving you a clear way of how do we even compute this, right? Because sure, you have a function over here. If I plug in everything, how am I even supposed to integrate this, or like just is there a general procedure how that I'm supposed to follow? I've answered none of that. I've basically just thrown a bunch of formulas at you over and over again. So now what I'm going to do is I'm going to take a different approach to defining this thing. And this depends on the fact if I know, this depends on the fact key, can I solve the fractional derivative? Okay, let's not take d of minus alpha anymore. Let's just take d of alpha, okay? So some alpha belongs to reals. So now I'm talking about a general real number, okay? So I want to take the derivative of this, and I want to answer the question key, what happens when f of x is equal to some power of x? So let's just take k, okay? So for now, for like just for understanding, you can take examples like x square or x cube, but this thing will also apply to something like x1 by 2 or x to the power of pi. Okay, so k is also real because gamma is defined for all real numbers, so we're good to go. And so the question is, what happens when I put my RL derivative on top of this? And through some working, or if you just Google, you can find out that your answer is given by d to the alpha dx alpha x to the power of k, which is our function that we're interested in, and this derivative is given by 1 by, alright, gamma on top. Yeah, so gamma of k plus 1 the whole divided by gamma of n, no, k minus alpha plus 1, yeah, and this is x to the power of k minus alpha. Yes, so yes, this is much nicer because k is given to you, k, it is known. Alpha is also given to you, this is also known. So in some sense, this is just a big constant or a scalar, right? And this power is also easy only, and so this whole derivative is pretty nice. Okay, we like this, and we would ideally like to use this as a shortcut to compute our RL derivatives. So that's exactly what we're gonna do. I couldn't find a general name for it, but I don't think the idea is that uncommon that it's not already discovered. So it's probably being used, it just doesn't have a standard name yet. So I'm gonna go ahead and give it one. So we're going to, okay, let's not say we're giving it one, but yeah. Now we're going to talk about the Taylor series, and that's our next ingredient, right? So we know how to take the derivative of d alpha dx alpha of x of k, right? We know how to do this. Now the next ingredient of our new way of defining fractional derivatives for a general function is the Taylor series. So what is the Taylor series? So the Taylor series is just if you have a function f of x. Yeah, is that right? Yes. So it is an expansion in terms of polynomials where I have an infinite sum that is just given by d n of f of x dxn into Oh my bad, not x, fa. So this is a function approximated at a point A. And if you want to approximate near the origin, then that implies that A is equal to 0. Okay, so it's simple. This is also simple, this is also simple. So yeah, the nth derivative of f evaluated at the point A. So that into x minus a to the power of n. And so for simplicity's sake, let's just say f of x at A origin. So A equals 0. And let's just take this as our function, okay? 0 dn of f of 0 divided by dxn and x to the power of n. Okay, so now using this, I wonder if it's clear, but if it isn't, this is now the part where I will write. Okay, great. Yeah, okay. So now we're going to be talking about the Taylor, to add a third name, Riemann Louisville derivative. And so this is going to be very simple. All we're going to do is we're going to combine our two elements so far. So our function now, d of alpha of f of x by d of x alpha is given by the infinite sum from n equals to 0 d to the power of n f of a. Let's keep it general only, let's not consider the origin right now. X to the power of n into 1 by, oh yes, I forgot to include the 1 by n factorial term in the Taylor series. Let me just go back and fix that now. Where is it? Yeah, over here. Divided by n factorial. Yeah. All good. Okay, so into n factorial, and now the inside part gets differentiated. So we have d of alpha. This is because, you know, everything over here is just a constant. So dx of alpha into alpha into x minus a to the power of n. This is the only part that we're actually differentiating. It would be wonderful if this thing clicked. Yes, okay, great. Okay. So, this is again not very hard to see. Yeah, let me just scroll down here. So what I get d alpha f of x is given by the infinite sum n equals 0, and now yes, I have the same dn of f of a the whole divided by dx of n into 1 by n factorial into gamma of n plus 1 divided by gamma of n minus alpha plus 1 into x minus a the whole power n minus alpha. So the reason why it's x minus a is all I do is I take a variable change, so I let x minus a is equal to t, and then similarly I just take d of what do you say, not d of t, d of alpha by dx alpha. So I just, dx is equal to dt only. So if I just substitute that, I just get t over here, and I get, oh, I didn't mean to move myself, okay, yeah, and you just get t, right, t to the power of n. So that's why it's still x minus a over here. So yeah, we know that gamma of n plus 1 is equal to n factorial. So that's why our term gets very simple. It's equal to d of n f of a dx of n into 1 by gamma n minus alpha plus 1 into x minus a n minus alpha. Okay, so this is how you take the fractional derivative of a function using Taylor series. Alright, now what is tropicalization? Okay, what is the tropical part? So depending on the value of alpha, whoa, what's happening now? Whoa, okay, crazy. I need to erase that. What's going on? Let's write in red now, just for a change of scenery. Or let's write in green, because now the tropical part is coming. So depending on the value of alpha, we will have different priorities. So if alpha is equal to an integer, you just get your regular Taylor series. If alpha is equal to rational, then the right hand side, the RHS of this expansion, is going to be a rational powered polynomial. Yeah, makes sense, because this part over here becomes a fraction. So we will have to study not rational powered polynomials. Similarly, if r is equal to real, then we'll have to worry about real numbers as the degree of our polynomial. And lastly, if alpha is equal to a complex number or anything else, any arbitrary field, then we have to talk about complex slash field of scalars. So this is one particular type of research you can carry out. You can look into the types of polynomials that we get for elementary functions. Things like sine, cos, tan, log, e to the x, and so on. Okay, so these are your elementary functions, and you can go ahead and apply your fractional derivative on all of these, and instead of computing them via the regular RL method over there, you can try out this method of using the Taylor series to approximate it, and you can study the polynomials you get under this specific part, and that will be things of interest, things you can say about just the number of roots of your polynomial when alpha is equal to rational. Does it still hold under the fundamental mental theorem of algebra. These are interesting things you can explore. And if you're daring, you can see if it explores not only for the rational case, but for the real and for a more advanced project, you can check out what happens in the complex ordered polynomials. Okay, so I'm not even sure. Okay, so I'm sure rational powered polynomials exist. This I'm pretty sure has quite a bit of study done on it. I am not really sure about real because that would include irrational powers. And I'm certain there hasn't been much done about complex ordered. So an example of a complex ordered polynomial would be like, x to the power of I plus 3x to the power of I plus 2i. Let's put 2i over here just for the sake of it. And plus 4 is equal to 0. So how many roots? Does this polynomial have? Where do these roots even lie? Where are the roots? Do I get all of my roots for free in complex numbers? Do I have to go to some higher dimensional field to get my roots of this complex ordered polynomial? We don't know. And maybe there's some structure to study when it comes to the one specifically induced by our Taylor series. Okay, and this is one potential thing that you can work on. Now we're going to talk about the tropical part. So we've just talked about differential operators, right? So far, tropical differential operators. So far we've talked about differential operators. That's okay. We understood that. Now we need to talk about tropical. So what does tropical mean? So when we talk about tropical, we're talking mainly about tropical geometry. It is a subfield that comes from a field called algebraic geometry. And what we're going to be doing under this is we're going to be studying tropical polynomials. Or more formally, they're called varieties instead of polynomials. You can think of them, or what we're studying is varieties instead of polynomials. So what is tropicalization? Yeah. Okay, so the main object of study or the main focus is something called a tropical semi-ring. And what this tropical semi-ring does is it allows you to do a certain process called tropicalization. What does tropicalization do? I'm just throwing words around, right? So tropicalization allows you to turn addition in your polynomial to maximum. What does that mean? And I'm just going to continue anyway without answering for now. And it takes multiplication and converts it to addition. And now you're probably confused because it doesn't immediately register what that means, right? So let me take some examples. Because it's much easier to explain via examples rather than worrying about the whole formalism of how we even define this. It's best understood with examples. So what it does is it takes multiplication to addition, right? So y into x goes to y plus x. Okay, this is what tropicalization does. Trop. Similarly, y plus x under tropicalization takes you to the maximum of y comma x. Okay. So far, I'm going to keep throwing more examples. If I take y square under tropicalization, it's going to take me to y plus y, which is equal to 2y. Similarly, if I take yn under tropicalization, it's going to take me to ny. Now, more examples. If I take 2y and I take it under tropicalization, it's going to give me 2 plus y. And if I take 2 plus y under tropicalization, it's going to give me maximum of 2 comma y. Okay, so I hope these examples help you understand exactly what we're doing. And let's take a little more complicated example where it'll sort of make a lot more sense. So say I have something x to the power of 5 plus a x to the power of 4 plus bx plus c, and I want to tropicalize this. So let's do this step by step, right? We know that if I take yn, it goes to ny, right, under tropicalization. So similarly, x to the power of 5 is going to go to 5x, okay, and so on. I'm going to do the same for the others. Okay, so a to the power of x4 takes you, I'm not going to write trop under everything, takes you to, it's going to convert addition in multiplication between these two into addition, so that becomes a plus, now x to the power of 4 under tropicalization becomes 4x. Okay, similarly bx is going to become b plus x, okay, and c remains as c. Okay, now all of these are under addition, so this converts it to the maximum under tropicalization. So instead, I'm going to take one big max over here, and I'm going to take from n equals 0, no, not from n equals 0, I'm going to take one big max over here, and I'm going to take all of these terms on the right hand side. So 5x, comma a plus 4x, comma b plus x, comma c. So easy, right? I hope this big example at the end sort of helped you build up to it. And now, for a general case, say I have some summation, some polynomial, given as p of x is equal to the summation over I equal 1 or I equal 0 all the way to I equal n. Our polynomial p of x is given by some coefficient ai and x to the power of I. Now if I tropicalize this thing, tropicalization, so what does that do? It turns my summation into one big max, or I could even write it as tropical addition, and it's going to take the set of all the terms and it's going to find the max in that. So all the normal terms are given by ai into x to the power of I, right? So more generally I can express it as ai plus x to the plus ix for I equal 0 to n, or I can write it like this: I equals 0 n ai plus ix. So this is the general notation, okay? This addition sign you'll see often. So if you read papers, you'll just see max or this big circle and plus or this wedge like thing as basically interchangeably. So these all mean the same thing. tropical addition. Similarly, you'll only see one thing for tropical multiplication. Or maybe two. So that is this thing and your regular addition. So this is what tropicalization does, right? It takes your regular addition and converts it to tropical addition. And it takes your regular multiplication and converts it to tropical multiplication. Now tropical multiplication and tropical addition are both individually the same as taking the max and taking the sum. So this is the real action, or not the real action, the true action of tropicalization. This is a casual phrase I'm throwing out. It's not exactly a standard term or a official way to refer to it. But yeah, this is just what I want you to think is really going on. I may have the fastest laptop on the planet. Okay, great. Yeah, so with that out of the way, we know how to take the tropicalization of a polynomial p of x. So we're going to do that to our tropicalization of our Taylor-Riemann-Liouville derivative. So what we say is that, where is it? Right. Okay. So the tropical derivative of f of x is given by the trop of d alpha by dx alpha f of x, which is equal to the max of the set that contains the terms d n f by dx n minus gamma n minus alpha plus 1 plus n minus alpha into x minus a. So it takes all these terms from n equals to 0 to infinity. Okay, so this is your sum, and this is what my idea of the tropical derivative is. Now, yes, okay, so we've sort of understood what tropical derivative means, right? Now what we need to know is, what does it mean to take a tropical differential operator, right? So differential operator in the sense, if I take different values of alpha, then I get what do you say, so for rationals I'm going to get one kind of operator, for reals I'm going to get one kind of operator, if I take complex numbers I take one kind of operator, or if I take any other arbitrary field then I get that kind of differential operator. So this is one way to generalize your differential operator, starting from a derivative, and if you like you can focus on that in your research. Or now differential operators, some of them or most of them actually can be given as ODEs. So if you have an ordinary differential equation, so a standard example or a simple example to understand is the Schwarzian derivative. Schwarz derivative. And I will explain that below. But basically, we say if I have an differential operator, I can find its corresponding ODE, and I can chuck in my function f of x, and I can spit out a ODE of f of x as a function. Okay, and lastly, I can think about matrix differential operators. Now, this is a more commonly used, like a more commonly seen version of differential operators. And the idea is that almost every ODE can be mapped to its matrix differential operator. This works for all of them, but only most of the matrix operators can be mapped back to its corresponding ODE. So we will be looking at the matrix operators that we can map back. We're going to try to say something about which matrix operators can be mapped back to an ODE. And if we find that almost all, instead of just most, if we find that all of them can, then we can directly convert any matrix or differential operator into a corresponding tropical operator just by changing what we mean by ODE. Okay, so now I'm going to explain what we know about from the ODE perspective. Scroll down. Thank you. Yeah, okay. So now I'm going to talk about one typical one that I encounter quite a lot, and it's called, not, I don't really encounter it quite a lot, but it is encountered quite a lot, not by me. Schwarz derivative. So this was mainly developed in physics for general relativity. Okay, and this is why it's relevant. So a little bit on the usefulness of tropicalizing something. So we're going to be talking about what's the point. And so this is going to have to do about its roots, right? Tropical geometry is a subfield of something called algebraic geometry. And in algebraic geometry, we often encounter, we're studying basically the solutions of really high ordered equations, say, I don't know, y7 of z plus xyz equals 0. So we want to find out the solutions of this. And as you can see, the exponents here are crazy. So this is very nonlinear. Right. So what do? We simplify it. So what tropical geometry does, if this is my polynomial p of x, tropical geometry takes p of x and linearizes it. So it loses some information, but it keeps enough for you to just know some basic things like intersections with other polynomials. Say you had p of x and q of x, and if you applied tropicalization to both of them, then let's just put it as t of p and t of q, then the number of intersections between these two is still preserved. So that is good. You can study really simple things by, instead of taking this massive nonlinear equation, you can break it down and then you can study its basic properties. So that helps for the start of any question. If you're interested in algebraic geometry, that helps you get some basic information of what you're working on. For us, what we're interested in is we're interested in applying this to any GR calculation, general relativity. So yeah, that's why we're going to just apply this to, first we're going to apply this to the Schwarz derivative. So the Schwarz derivative checks if any function f is a Mobius transform or not. So basically, if I take a function f of x, and I apply the Schwarzian derivative of it, I get, what is it, f3 of c, or no, x in this case, divided by f1 of z, or x in this case, minus 3 by 2 into f double dash of x and f dash of x, the whole squared. Okay, so since we have well defined the tropical derivative for d alpha of f of x by dx alpha, so all we have to do is, for this case we have to put alpha equal 1, this case we have to put alpha equal to 3, equal to 3, this one alpha equal to, this one again alpha equal 3, alpha equal 1, and yeah, we check in the tropicalized versions of each of these and we solve this and we're done. So we can explore this as well. This is also going to be an area of our research. Is this a good approximation? Is it bad? Should we first take the derivatives and then apply the tropicalization on this part? So these are the kind of questions we'll be looking at. So this will be the third thing that you can research under this project. So before I end this video, I will list out everything. So research interests, research aims of this project. So first we need to see what happens when alpha belongs to an arbitrary field f. Next we need to see can all matrix differential operators we convert into ODEs, and that's probably true. We need to prove that all matrix operators can be converted to ODEs, and yeah, if we can, Then we need to take some classic examples. And we need to tropicalize them, and we need to study its counterpart. And lastly, we take the Schwarz derivative, and we see if the tropical Schwarz derivative gives either a good bound or a good approximation. We hope it's at least a good bound, because if we can say ki, okay, most definitely the Schwarz derivative of f of x is greater than or lesser than, strictly greater than or lesser than the tropical of s of f, then that would be really nice. But if we don't, then it would be better to focus on this question first and then try to answer this one. Because if the tropical Schwarz derivative does not work as much as it could, or does not provide any good bounds, then it's useless to look at matrix differential operators and their corresponding ODEs and then to tropicalize this. Okay. A safe exploration is this one. Just see what happens when alpha is real or complex or anything exotic like quaternions, octonions, rationals with some extension, right? So all of these are interesting and safe questions to explore. If you want to check the validity of this question, so this is 2, this is 1, and this is 3. So if you want to check the validity of our second question, then first you're going to have to focus on 3. And 1 is independent of 2 and 3, so you can pursue 1 regardless. And that's it for the intro to tropical differential operators. And I hope to see I hope to see people just leaving a comment. So you can leave a comment with your email, and yeah, I will text you back and we can work out things from there. So thank you for listening.